Math 1, Worksheet 5.2G. These are going to be the solutions. Started off, joke of the day. All right, so what does the Secret Service yell when they want the president to get down in case of an attack? Donald Duck. Get it? Mason, explain it to Kylie. Thank you. Okay, so here we go with our solutions to this worksheet. So in numbers 1 through 6, we're going to be determining whether each table or rule represents a linear or an exponential function, and then we're going to explain. Okay, so when you have a table, what you want to do is you want to take a look at the x values and see if they're all increasing by the same amount, and you can see that each x value from 1 to 2, from 2 to 3, from 3 to 4, these are all increasing by 1. And then you also want to take a look at the y values. So you can see the y values to get from 3 to 9, that's increasing. To get from 9 to 27, that's increasing. And to get from 27 to 81, we are increasing, okay? But we're increasing by a multiplication factor of 3, okay? So when the y values are increasing by a multiplication factor, okay, in other words, if you're multiplying to get from the first number to the second number to the third number, and so on, and if you're multiplying by the same amount, this would make this an exponential function. So number 1 is going to be exponential. Okay, when we look at number 2, we look at the x values. We could see that each x value is increasing from 1 to 2, from 2 to 3, from 3 to 4, and they're all increasing by 1. And then we look at the y values, and you can see we go from 3 to 9, so that's increasing. We go from 9 to 15, that's increasing, and we go from 15 to 21. So each value is increasing, and if you notice, we're increasing by adding 6. 3 plus 6 is 9. If we add 6 again, 9 plus 16 is 25. If we add 6 again, 15 plus 6 is 21. This is called a common difference. Okay, so when you're adding or subtracting to get from one value to the next value in a table, it is what is known as a common difference. If you have a common difference, then it means that it is a linear function. So number 2 is linear. Number 3, the function is y equals 5 times 2 to the x power. This would be exponential, and how the reason why we know it's exponential is because of the x right there. If the x is an exponent, it is exponential. So x is an exponent. Anytime x is an exponent, it makes the function exponential. Okay, we have number 4 right here. We have y is equal to 6 times x to the third power. All right, this equation or this rule right here would also be exponential. Why do we know it's exponential? Because we have an exponent of 3. Okay, so anytime you have an exponent of 3, whether it's a number or whether it's a variable, it's going to be exponential. In number 5, you see the rule is y equals 3 times x minus 8, or 3x minus 8. There are no exponents at all, so this would be linear. Okay, no exponents. That's how we know that the function in this case is linear. Number 6, you see in the function right here we have an exponent. Even though that it's an exponent of x, anytime you have an exponent, it makes the function exponential. Okay, and the reason is x is an exponent. All right. Okay, number 7 and 8, which we were supposed to do, you want to evaluate each function for the given value. So what we're going to do in number 7 is our function is f of x is equal to 5 to the x power, and we're going to substitute 4 in the place of x. So to evaluate this, my function will become f of x is equal to 5 to the 4th power. To evaluate that, I just multiply 5 by itself 4 times. So this would be equal to 5 times 5 times 5 times 5. So number 7 is 625. In number 8, I'm evaluating the function h of t is equal to 3 times 4 to the t power for t is equal to negative 3. So to evaluate this, I'm going to substitute negative 3 in the place of t in my function. So I'm going to evaluate 3 times 4 to the negative third power. Okay, rewriting this problem so that to evaluate it, I have to rewrite the problem so there's no exponent or negative exponents. So 4 to the negative third power becomes 1 over 4 to the third power. Then I evaluate the exponent, so this would become 3 times 1 over 4 to the third power is 4 times 4 times 4, so that's 64, and I multiply this out, so I get 3 64ths. And I cannot reduce that, so that would be the answer to number 8. Okay, number 10. We want to graph each exponential function. So in order to graph a function like number 10, remember what we want to do is that we want to probably use graphing paper, which I have right here. And the first thing that you want to do is that you want to create a table. So you want to create a t-table or an xy table. And what we're going to do is we're going to pick some values for x. And I'm going to pick 5 values for x, so I'm going to pick negative 2, negative 1, 0, 1, and 2, and I'm going to plug each one of those values or substitute each one of those values into the equation or the function, and then I'm going to use the results in order for me to generate a graph, and I'm going to generate points that I'm going to plot on a graph here, over here, okay? So substituting negative 2 in the place of x, my function for y would become 3 to the negative 2 power. Then I evaluate that. I have to rewrite it so there are no negative exponents, so that would be 3 to the 1 over 3 to the positive 2 power, which is 1/9. So that means when my x value is 2, my y value is 1/9. And then I'm going to go over here and I'm going to plot that point on my graph. So I'm going to go to negative 2 on the x, and then I'm going to go up 1/9 of a spot, which is barely going up above what would be 0. Okay, now I'm going to substitute, I'm going to go back to my table, and now I'm going to substitute in negative 1 for my y function. Rewriting this, so I don't have a negative exponent, that would become 1 over 3 to the 1 power, which is just 1/3. So when x is negative 1, my y value is positive 1/3, and I plot that point. Go to negative 1 on the x, and then I'm going to go up a third of one space up, basically. So there's negative 2, there's negative 1. Continuing the process, I'm now going to substitute 0, so my y function would become 3 to the 0 power. Evaluate that, that's equal to 1. My next point that I'm going to plot is 0, 1. So I'm going to go over 0, I'm going to go up 1. Put a point. I'm going to evaluate now my y function when x is 1. So my function would be 3 to the 1 power, which is equal to 3. So then I plot the point. When x is 1, y is 3. Go to where x is 1, I'm going to go up 1, 2, 3 spots on the y-axis and put a point. And lastly, I'm going to evaluate my y function for when x is 2, so I get 3 to the 2nd power, that's equal to 9. And I'm going to plot the point when x is 2, y is 9. So I'm going to go over to 2 on the x, and then I'm going to go up 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see that my points are not lying in a straight line, so this means this is not linear, but if I connect my points, I can connect them with a nice smooth curve. This would be an indication of what an exponential function's graph would look like. Extend the graph up a little bit, and then extend the graph going down a little bit each way with arrows. Okay, so that's what number 10 would have looked like. Okay, skipping down to number 14, an investment of $8,000 in a certain certificate of deposit known as a CD doubles in value every 7 years. The function that models the growth of this investment is f of x is equal to 8,000 times 2 to the x power, where x is the number of doubling periods. If the investor does not withdraw any money from this CD, how much will be available for withdrawal after 28 years? Okay, so x represents the number of doubling periods. It tells me in the problem that this CD, the certificate of deposit, doubles every 7 years. Okay, so I'm going to figure out how much money will be available for withdrawal after 28 years. So how much money after 28 years? Okay, so x is going to be how many 7-year periods there are in 28. Okay, well, since 7 times 4 is equal to 28, that means in this problem that is your x value. There are 4 7-year periods in 28. So to figure out how much money, what we would do is we would take our function f of x is equal to 8,000 times 2, but instead of the x power, we're going to have a 4 power. And then we evaluate this function here to the problem, okay? So working out the exponent first, I'm not going to do anything with the 8,000. 2 to the 4th power is 2 times 2 is 4, times 2 is 8, is times 2 is 16. And then I'm going to multiply out 8,000 times 16. And you can see I've got a calculator right here which would help me out. So 8,000 times 16 is 128,000. Okay, so that means the answer would be 128,000 for number 14. Okay, number 15, we're reading the problem, and then we're figuring out what pertinent information we need to know. A population of amoebas in a petri dish will triple in size every 20 minutes. At the start of an experiment, the population is 800. The function y equals 800 times 3 to the x power, where x is the number of 20-minute periods. So we know x stands for 20-minute periods, models the population growth. How many amoebas are in the petri dish after 3 hours? So we're trying to figure out how many amoebas are there in 3 hours, okay? We know that in this problem, x is equal to 20-minute periods. So what we need to do is we need to figure out how many 20-minute periods are there in 3 hours. In other words, how many 20 minutes are there to get to 3 hours, okay? Well, there's 60 minutes in an hour, so that means there's 3 20-minute periods per hour. So that means there's 9 20-minute periods in 3 hours. So x is going to be equal to 9. Okay, now how do we know that? Well, if we take 20 and we multiply it by 9, that's 180, and that would be 180 minutes, which is 3 hours. So x is going to be equal to 9. So then to figure out the population, or how many amoebas there are, we take my function y is equal to 8. Whoa, my lights just went off again. Hold on, I gotta walk around. There we go. There's nobody in the classroom, so the lights go off on me if I'm just standing here talking. So anyhow, I'm gonna take 800. I'm gonna multiply it by 3, and then it's gonna be to the x power, but we just determined that x is 9. Okay, evaluating this, I have to work out the exponent first. So 3 to the 9th power. You can see I'm working it out on my calculator here. So 3 to the 9th power is 19,683. And then I multiply that by 800. So that means that there are that many amoebas, and that's a lot of amoebas. So what is that going to be? 15,746,400 amoebas in the dish after 3 hours. Okay? All right, turning it over. The last problem you had to do was number 17. So So in number 17, we wanted to evaluate each function over the domain from -2 to +3, and then we wanted to answer the question, as the values of the domain increase, do the values of the range increase or decrease? So what we're doing in this problem is that we are going to substitute each one of these 6 values into my function. Okay, so my first value that I would evaluate, and I'm going to evaluate that. So I'm going to substitute -2 into my function, and I'm going to see what that equals. Rewriting this problem so that I don't have negative exponents, I would get 1/3 to the second. So that means my first value is my range, or my first value is 1/9, and each answer that I get is going to be representative of what my range is. Okay? Next, I'm going to evaluate when x becomes -1. So my function would become 3 to the -1 power, which, rewriting that, would be 1/3 to the +1 power, which is 1/3. Okay, my next domain value I'm going to substitute in would be when x is 0. So that means my function would be 3 to the 0 power, which is equal to 1. So right now my range went from 1/9 to 1/3 to 1. Now I'm going to evaluate it when x is equal to 1. So my function would become 3 to the 1 power, and that is equal to 3. Evaluating my function when x is equal to 2, my function will become 3 to the 2nd power, that is equal to 9. And lastly, I'm going to evaluate my function when x is equal to 3. That makes my function 3 to the 3rd power, which is equal to 27. So you can see my range starts at 1/9, it goes to 1/3, it goes to 1, then to 3, then to 9, then to 27. So now we can answer the question, as the values of the domain increase, do the values of the range increase or decrease? I am increasing, each value is getting a little bit bigger, so the range is increasing.